In this video, let us first discuss what cyclic coordinates are. If Lagrangian contains velocity, if Lagrangian contains qi dot, but qi is missing, then qi is called cyclic coordinate. If Lagrangian contains velocity but corresponding coordinate is missing, then that coordinate is called cyclic coordinate. To get more clarity, let us discuss an example. A particle is undergoing projectile motion. Let's say its position is denoted by x and y. Then the Lagrangian will be equal to half m x dot square plus y dot square minus mgy. Why there is only x dot square and y dot square in kinetic energy? Because the motion is restricted to 2 dimension. The projectile motion is a 2D motion. Therefore, we have only half m x dot square plus y dot square in kinetic energy. And potential energy is mgy. So when you subtract it, you will get the Lagrangian to be like this. Now, as you can see, x dot is present in the Lagrangian, but x is not present. Therefore, x is the cyclic coordinate. X is cyclic. Now, why do we discuss cyclic coordinates? What is the importance of cyclic coordinates? Importance is that for cyclic coordinates, corresponding generalized momentum is conserved. So when x is missing in this example, in the Lagrangian x is missing, therefore del L upon del x equal to 0. And from Euler-Lagrange equation of motion, we can write d by dt of del L upon del x dot minus del L upon del x is minus 0. This is equal to 0. This implies d by dt of del L upon del x dot is generalized momentum corresponding to x, which is px. This is equal to 0. And this implies px is equal to constant. Therefore, if x is cyclic, corresponding momentum, which is px, will be conserved. This is the importance of discussing cyclic coordinates. In this problem, px is equal to del L upon del x dot is equal to mx dot is equal to constant. And m is already constant, therefore x dot is constant. Now we are going to discuss the gauge transformation of Lagrangian, but before that, let us focus on a problem. Here is a problem from CSIR NET December 2015. Here we are given a Lagrangian in Cartesian coordinates. We have to find out the expression for canonical momentum PR in polar coordinates. I hope you know what polar coordinates are. In the plane polar coordinate system, which is a 2D coordinate system, to represent the position of a particle or a point, we use the radial distance from the pole or the origin. It is called r. And the angle measured from the positive x-axis, this is called theta. So to represent the position of a particle, we can use these coordinates r and theta, and it is related to the Cartesian coordinates using the relation x is equal to r cos theta and y is equal to r sin theta. Therefore x dot is equal to, this is total time derivative of x. Therefore, first we have to take derivative of r multiplied by cos theta plus r times derivative of cos theta, which is minus sin theta theta dot. And y dot is equal to r dot sin theta plus r times derivative of sin theta is cos theta theta dot. Now in the expression for Lagrangian, you have to put, instead of x dot, you have to put r dot cos theta minus r sin theta theta dot, and instead of y dot, you have to put r dot sin theta plus r cos theta theta dot. Instead of x square, you have to put r square cos square theta, and instead of y square, you have to put r square sine square theta. Then you will get Lagrangian is equal to, now why are we expressing Lagrangian in terms of polar coordinates? Because in the question we are asked PR, and PR is equal to del L upon del R dot. And to find this, first we need to express L in terms of polar coordinates. So let us substitute these things, x dot y dot in L. L is equal to x dot y dot minus x square minus y square. This is equal to x dot y dot minus x square plus y square, and in polar coordinates r is equal to root of x square plus y square. Therefore x square plus y square is equal to r square. So this thing right here is r square. L is equal to x dot is r dot cos theta minus r sin theta dot times y dot is r dot sin theta plus r cos theta dot minus r square. This is the Lagrangian. Now we need PR. PR is equal to del L upon del R dot. This is equal to cos theta times r dot sin theta plus r cos theta dot plus, so you differentiated this with respect to r dot partially and then multiplied with this. Now you have to differentiate this and then multiply by this. So when you differentiate the second term, you will get sin theta. This is partial differentiation times, now you have to multiply by first term, r dot cos theta minus r sin theta dot. This is equal to, now cos theta r dot sin theta is occurring 2 times. Therefore you can write 2 r dot cos theta sin theta plus r theta dot cos square theta minus sin square theta. Cos square theta minus sin square theta is cos 2 theta, and 2 cos theta sin theta is sin 2 theta. 2 cos theta sin theta is sin 2 theta. Therefore we have PR is equal to r dot sin 2 theta plus r theta dot cos 2 theta. The correct option here is option 4, r dot sin 2 theta plus r theta dot cos 2 theta. Now let us move on to discuss what gauge transformation of Lagrangian is. So there is a Lagrangian L. We are transforming it into a new Lagrangian L prime. L prime is equal to L plus d by dt of f of q and t. So there is a function f which is a function of coordinate and time. We are taking its total time derivative and then we are adding it to the Lagrangian. Then we will get a new Lagrangian L prime, and if we are using this L prime and we are putting it into Euler-Lagrange equation, then we will get some equation of motion. Let's say this is equation of motion 1, and if we put L into Euler-Lagrange equation, then also we will get an equation of motion. Let's say that equation of motion is equation of motion 2. Then we are saying that 1 and 2 are same. 1 and 2 are same. In simple words, gauge transformation of Lagrangian is such a transformation of L due to which equation of motion does not change. Now let us discuss an example. Let's say the new Lagrangian that we have is equal to old Lagrangian plus q dot e raised to q. The question is, does this change equation of motion? We have to only check if q dot e raised to q can be written as total time derivative of some function of q and t. Clearly, if we choose f is equal to e raised to q, then d by dt of f is equal to d by dt of e raised to q, which is equal to e raised to q times dq upon dt, which is equal to e raised to q dot. Therefore, we can write q dot e raised to q as the derivative of total time derivative of some function which is a function of q and t only. E raised to q is a function of q and t only. Therefore, this is a gauge transformation of Lagrangian, and this means equation of motion does not change. Equation of motion does not change. Now let us move on to another problem related to constraints. This was asked in June 2023 NET exam. Here we have a one-dimensional rigid rod. It is constrained to move inside a sphere. So we have a sphere here, and there is a rod. The rod is rigid, and it is said that its two ends are always in contact with the surface. So at no point in time it will be like this. Always its end will touch the surface. Both ends will touch the surface. We are asked to calculate the number of constraints on the Cartesian coordinates of the endpoints of the rod. Let's say this is the center of the sphere. For the end point of rigid rod, one end point, let's say the Cartesian coordinates are x2, y2, z2. Another point, it is denoted by x1, y1, z1. And center is at origin. Center of the sphere is at 0, 0, 0. Therefore, one of the constraints is that the length of the rod is always same. That is what we mean when we say it is rigid rod. Therefore, we can write x2 minus x1 the whole square plus y2 minus y1 the whole square plus z2 minus z1 the whole square. This is equal to L square. That is, length of the rod is always same. Now another constraint is that this distance, the distance between end point of the rod and the center of the sphere, it will always be equal to r. Therefore, I can write x1 minus 0 the whole square plus y1 minus 0 the whole square plus z1 minus 0 the whole square is equal to r square. Similarly, I can write for this endpoint as well. At any point of time, the distance between one end of the rod and the center of the sphere will be r, because it is said that the two ends are always in contact with the surface. Therefore, we have third constraint, which is equal to x2 minus 0 the whole square plus y2 minus 0 the whole square plus z2 minus 0 the whole square. This is also equal to r square. So these are the three constraints in the case of a rigid rod which is connected to the surface. Two ends are always connected to the surface. 3 is the correct answer here. Now before concluding this lecture, let's familiarize ourselves with the formula of kinetic energy in different coordinate system. Formula of kinetic energy in different coordinate system. This can be helpful in certain situations. First of all, in Cartesian, we have the line element or infinitesimal displacement dl is equal to dx I cap plus dy j cap plus dz k cap. If we divide by dt on both sides, we get dl by dt is v is equal to dx by dt is x dot I cap plus dy by dt is y dot j cap plus dz by dt is z dot k cap. Now modulus of velocity is equal to x dot square plus y dot square plus z dot square. You take component of each and square them and add them, then take root, you will get modulus of v. V square is equal to modulus of v the whole square is equal to x dot square plus y dot square plus z dot square. Kinetic energy is therefore in Cartesian coordinate system 1 by 2 m x dot square plus y dot square plus z dot square. This is in 3D. If it is in 2D, you will have half m x dot square plus y dot square in 2D, and in 1D you have half m x dot square. In spherical polar coordinate system, we have line element dl is equal to dr r cap plus r d theta theta cap plus r sin theta d phi phi cap. Divide by dt, we get v is equal to r dot r cap plus r theta dot theta cap, d theta by dt is theta dot plus r sin theta d phi by dt is phi dot, r sin theta phi dot phi cap. This is velocity. Kinetic energy is equal to half mv square. V square is r dot square plus r square theta dot square plus r square sin square theta phi dot square. In the case of cylindrical coordinate system, we have dl is equal to, this is spherical and here we have cylindrical. In cylindrical coordinate system, dl is equal to dr r cap plus r d phi phi cap plus dz z cap. Divide by dt, we will get v is equal to r dot r cap plus r phi dot phi cap plus z dot z cap. V square is equal to r dot square plus r square phi dot square, r square phi dot square plus z dot square. Therefore kinetic energy is equal to half m r dot square plus r square phi dot square plus z dot square. So these are the formulas for kinetic energy in cylindrical and spherical coordinate systems. Before concluding this lecture, I want to add one more point related to gauge transformation of Lagrangian. So when we were discussing gauge transformation of Lagrangian, we said that if L prime is equal to L plus small f, and if we can write small f as total time derivative of some capital F which is a function of q and t, then the equation of motion does not change. This is the case when f is a function of q, q dot and t. Now suppose if we have L prime is equal to L plus some g, where g is a function of q, q double dot, q dot t, then instead of checking if we can write as total time derivative of capital F, we check if d square by dt square of del g upon del q double dot minus d by dt of del g upon del q dot plus del g upon del q is equal to 0 or not. So you need to check if d square by dt square del g upon del q double dot minus d by dt of del g upon del q dot plus del g upon del q is equal to 0 or not. If it is 0, if equal to 0, equation of motion does not change. And if it is not equal to 0, equation of motion changes. We can do a problem related to this in the next lecture, possibly. If you found this video helpful, do not forget to smash that like button, and also if you have any doubts you can put it in the comment section. That's all, thank you.